Hello, everyone, and thank you for joining today's webinar on the multi-detector strategy for reducing response factor variation in E&L analysis. By way of introduction, today I'm going to begin by describing what we mean by response factor variation, and I'm going to discuss the two problems it creates in E&L analysis. The first one is its effect on the evaluation of the AET, and secondarily, we're going to talk about how it affects quantitative accuracy. We're then going to talk about how we apply a multi-detector solution to resolve this problem, which includes a triple detection LC system and a dual detection GC system. Now, when we think about extractables and leachables, the molecules that typically come to mind include things like antioxidants, slip agents, plasticizers, monomers, cross-linking agents, etc. But there are a number of other kinds of molecules that are very important and very frequently seen, but which are distinct because they are not intentionally added substances and they are generally not commercially available as standards. And this includes things like oligomers, polymerization side products, process impurities, and degradation products. And because we need to quantify and identify these species, not having commercially available standards is actually at the root of the response factor variation problem. Now, when we talk about response factors, I want to start by describing what we mean. So the response factor is the signal per unit concentration that you get for an individual compound. And here in the figure that you see on the screen, we actually have two different compounds present at the same concentration. But you'll notice that their peak areas are not the same. Compound 1 gives a much stronger response per unit concentration than compound 2. And this is what we mean by response factor variation. Now, I do want to also mention that this is not an unusual thing. In fact, most detectors do not provide an equal response for different compounds at the same concentration. So response factor variation is the norm, not the exception. I also want to define what we mean by the relative response factor, or RRF value. Today, we're going to be talking about RRF values for most of the remainder of this talk, so it's very important we have a good understanding of this topic. So the relative response factor can be defined as the slope of the calibration curve for our target compound divided by the slope of the calibration curve for our surrogate standard. And what we need to understand about RRF values is that when we have a RF value of 0.58, that means that any quantitation done with that surrogate standard will get a value that's only 58% of the true value. In other words, RRF values are directly correlated to quantitative accuracy. Now, another thing we need to understand is that the LOD is also affected by response factor variation. If we have a compound which has a low RRF value, then we're going to get a poor LOD for that compound because its response is weak. And so we need to be careful that when we choose our surrogate standards to establish our LOD, that we have compounds at a range of RRF values such that we can reflect the potential diversity of our extractables and leachables. Now, the question can be asked, how low do we need to go when we are doing an analytical evaluation of extractables and leachables? What is the correct LOD? And the industry has defined the analytical evaluation threshold, or AET, to answer this question. The equation is applied here, and we note that it contains a dose-based threshold as well as a series of parameters related to the device and the extraction process. And importantly, it also contains a UF, or uncertainty factor. Now, the purpose of the uncertainty factor is to account for response factor variation. Typically, this equation is defined as UF equals 1 divided by 1 minus RSD, where RSD is the relative standard deviation of the response factors for the distribution of all of the analytes being analyzed by the method. So how is this applied in practice? So once we have defined an AET, our next step is to run some standards and determine the peak height or peak area associated with the AET concentration. So here we can see in this slide that in red we have a chromatogram for an extractables sample, and in black we have a chromatogram for two potential surrogate standards. Now, the first of those surrogate standards shows the peak height indicated here by the blue arrow. And I would note that this is at 200 nanograms per mil. If, however, we look at this second standard, it is also at 200 nanograms per mil, but you'll notice that because of response factor variation, it has a different peak height. And that means that the compounds which are considered to be above the threshold will change depending upon which of these two standards I use to set the AET level. And here we show the additional peaks that would be included if we used the poorer responding of the two standards. Now you might ask, how significant is this problem in actual practice? And in 2018, we published a study in the Journal of Pharmaceutical and Biomedical Analysis where we showed how the number of compounds that is considered to be above the AET changes as a function of which standard was used. And you can see here that it is quite dramatic. We can go from a very low number of compounds to a very significant number of compounds just based on which standard was applied to set the AET threshold. So, bringing us back to the idea of the UF, can the UF be used to compensate for this response factor variation? And what we show in this figure is that on the y-axis we have response, and on the x-axis we have a number of different compounds. And for each one of the compounds, we show a blue square, which indicates the response of that particular compound. And you'll notice that some of the compounds are above the non-adjusted AET line, but many of them are below it, which means they would not be included in our study because they'd be perceived to be below the AET, when in fact they're at the AET concentration. Our intention with the UF then is to adjust down the location of the AET line so that we can capture all of the compounds which are at the AET concentration. Now that sounds good, but there is still another problem, and I want to show it to you in the above calculation. So here we have the AET equation, and we've applied the TTC value for a lifetime exposure of 1.5 micrograms per day. And we've used an extraction volume of 10 mils, which is a relatively small and conservative extraction volume. And we have a number of devices per patient of 1 and a concentration dilution factor of 1. And we're going to apply the frequently cited UF of 10. And we'll find that when we do that, we get a AET of 15 part per billion, or 0.015 micrograms per mil. This is in fact a very low concentration. And for those who are practitioners of LCMS, you will immediately recognize that we have a problem because most LCMSs in a screening mode cannot hit this detection limit. And so the only option we then have is to concentrate our extracts. But in concentrating the extracts, we may either volatilize off or degrade some of our extractables and leachables. So we have this conundrum of how can we be sufficiently protective while also making sure that we're not losing or degrading compounds during any concentration steps. So in summary of our RF problem number 1, which I will describe as AET underreporting, we can see that, that we need a universal method for analyzing extractables and leachables because we do not know in advance which kinds of compounds are going to be present. In other words, this is screening analysis. We don't have a subset of compounds we're looking for. We're just looking for anything that comes out of our device. When we do that, we note that if we have a UF that is not sufficient, we may not be sufficiently protective at the AET. However, if we do apply a large UF in order to compensate for that large response factor variation, we may extend beyond the sensitivity of the MS system, which could then require us to use concentration factors that could result in loss or degradation of our extractables. Lastly, I would also note that RF databases are very important as they allow us to calculate method-specific uncertainty factors. But I want to note they do not reduce the uncertainty factor. They just allow you to calculate what its value is. And so they are important, but not a solution to this problem. All right, let's talk about the second problem, which is quantitative inaccuracy. To demonstrate this issue, here again we have our chromatogram showing our internal standard and our target compound, and they're at equal concentrations. However, if we perform the calculation of the quantity of our target compound, we'll see that we get an artificially low value of 13.9 micrograms per mil because the response factor for our surrogate standard is actually stronger than that of our target compound. And this results in an inaccurate quantity. So in summary, in regards to the RF problem 2, the relative quantitation issue, we see that when the RF of the compound is less than the RF of the standard, we're not getting a worst case estimate of the concentration, and we're overestimating the LOQ of our compound. When the RF of the compound is greater than the RF of the standard, it is a worst case estimate. And this may seem like it's not as big a problem as the first case, but keep in mind that this could result in a margin of safety less than 1, which could cause us to reject an otherwise perfectly suitable device. Now, we would again note that RF databases are useful in that they allow us to correct for quantitative error for compounds in the database, but it only works for compounds in the database. So unless you have all of the necessary compounds in your database, this is not a solution in and of itself. We also note that UF factors do nothing to compensate for quantitative inaccuracy. They are only used in the AET calculation. All right, so we understand the problems. Let's talk about a solution. So today I'm going to be talking to you about the multi-detector approach for both AET evaluation as well as for quantitation. And I'm going to be describing 2 different chromatographic systems used for this purpose. The first is an LC system that contains a UV detector, a charged aerosol detector, and a QTOF LCMS detector. And we're going to run that in both positive and negative mode. So there are, in effect, 4 detectors used in the LC system. On the GC system, we'll use 2 detectors, MS and FID, or flame ionization detector. So we're going to get 2 signals for each compound in GC, 4 signals for each compound in LC, and we will use those to help us mitigate these problems. So here's an example of what the chromatograms look like for the 6 different detectors. And the first thing I want to point out is that the signals on each detector are orthogonal. What we mean by that is that they are uncorrelated one to another. You can have a weak response on one detector and a strong response on a different detector for the same compound. And that's because the principles of detection are distinct for the various detectors. The second thing we want to point out, which is very important to understand, is that we are not in any way combining these detectors other than to evaluate them individually and then use the sum total of all those results when evaluating at the AET. So, for instance, if we have a weak response on any one detector, we can compensate for that so long as there's a strong response on one of the other detectors. Because the only criteria that's required is that each compound be captured on at least one detector. And so long as it is captured on at least one detector, then that compound will be included in our study, and therefore that is the sufficient and necessary criteria. Now, we wanted to test the effectiveness of this strategy on a large data set to demonstrate how comprehensive it can be. And so we analyzed a database that was broadly constituted, made up of a variety of compounds relevant to medical devices. And that database of compounds had 217 unique compounds in it. We analyzed them on all 6 of the different detectors, and we made sure that the compounds had a very wide range of physiochemical properties, including a broad range of molecular weights from 93 to 1177 AMU, a wide range of log p values so that they would included both polar and nonpolar compounds, compounds of all different volatilities, from boiling points ranging from 102 to greater than 600. DBE from 0 to 20, meaning it had double bond equivalent values that ranged from no double bonds to a wide range of double bonds. And we included both acidic and basic species. So now I want to show you the results that we obtained for each one of the individual detectors for the database of compounds. And we're going to start with the LCMS detector in positive mode. Now, the LCMS system we were using was a electrospray ionization QTOF LCMS system. And this system has some excellent attributes for identification, including high mass accuracy and excellent sensitivity down to the picogram range. But we would note that it has a polynomial response. It is not a linear detector, strictly speaking, and that means the response factors will vary as a function of concentration. It is also subject to matrix effects. Here is the response factor distribution that we found for the LCMS positive mode detector. And I want to take a moment and just describe this graph in some detail because we're going to be looking at several of them. On the y-axis, we have the number of compounds that gave a particular range of responses. And on the x-axis, we have the RRF value. So if we see a range of 0 to 0.2, that means that nearly 40 compounds out of our database showed a response in this range. And when we think about what that means, for the LCMS positive mode, that means the majority of compounds, or the most abundant outcome, was to obtain a very poor response between 0 and 0.2. And we are comparing these to an average responding standard. Our second most abundant outcome is to obtain a very strong response, greater than 1.8. This obviously has significant implications in terms of the AET and in terms of quantitative accuracy when using LCMS positive mode. If we look at and calculate the RSD for this distribution, we see that the percent RSD is actually greater than 100%, which means we cannot calculate a suitable UF factor protective for this distribution. Now, if we then look at LCMS negative mode, we see a very similar distribution with a percent RSD that's again over 100%, meaning we also cannot calculate a protective UF for LCMS negative mode either. But there is one piece of good news. As I described earlier, in order to capture every compound, it is only necessary that each compound be successfully detected on at least one detector as above the AET. And we did note in this study that 54% of the compounds that were seen by LCMS were also seen in GCMS. And this means that for those compounds, we have the potential to capture them by the GCMS as well as by the orthogonal detectors, the UV or CAD, in LC. And if any one of those detectors captures the compound, then it will be successfully included in our study. So now let's take a look at the UV detector. Here we see that for UV detection, it's a completely different principle of detection. It's based on absorption of UV light. It is a highly linear detector. It's not subject to matrix effects and widely applicable to anything with a chromophore with nanogram level sensitivity. And we can see that the distribution for the UV detector at 230 nanometers is more Gaussian than what we saw for the LCMS. And if we calculate the percent RSD of this distribution, we see that it's only 60%, which means that we can calculate a protective UF at 2.5. So a much more reasonable UF than what was required for the LCMS detectors. Now let's turn our attention to the charged aerosol detector. This is again a completely orthogonal detector. It's good for measuring any non-volatile species. It is curvilinear, which means it has a fairly linear response, but not completely linear. It is highly precise and widely applicable with nanogram level sensitivity. But it is affected by the mobile phase composition. Here is our distribution for the CAD detector. And we can see that this distribution also has a most abundant response between 0 and 0.2. And while this may seem bad, there's one big difference between this and the LCMS detector. and that is that we can readily predict when this outcome will occur because volatile species cannot be successfully analyzed with the CAD detector in general. So being able to predict this allows us to know when this detector will be a good quantitative detector and when it will be a bad one. Now, if we use or calculate the RSD for this distribution, we get a value of 65%, and we can see that the UF value that's calculated is 2.9, which is again a reasonable UF value that can be applied for CAD detection. Now let's turn our attention to the GC detectors. The first detector we're going to look at is the electron ionization detector. It is an excellent detector for both identification and quantification. It's widely applicable, it's linear, it's got good precision generally, and it has nanogram level sensitivity. Here is the response factor distribution for GCMS, and we can see immediately that it is one of the nicest detectors from a response factor perspective. It has a percent RSD of 52%, which means our UF factor that's necessary is only 2.1. So it is a great detector from a response factor variation perspective. Also, I would note that in the few instances where it does have a very poor response, we found that 71% of the compounds detected by GC were also seen by at least one LC detector. And that means that if we do not detect a compound in GC, we have the opportunity to still capture that compound using one of those LC detectors, and therefore we can overcome that limitation for that compound. And typically this occurs when a compound is not very volatile. So for those non-volatile species, those are better detected by LC. And so right when the GC detector is weakest, the LC detector is strongest, and that allows us to compensate for those poor responding compounds. Now here is the flame ionization detector. This again, completely orthogonal. It measures any carbon-containing species. It has a nice linear response and is highly precise and is not subject to matrix effects in general. It is widely applicable with picogram level sensitivity and a very wide linear dynamic range. It is an excellent quantitative detector. Here is the response factor distribution for FID. We see that the percent RSD is 54%, which gives us a relatively low UF of 2.2, making it the second best detector from a response factor variation perspective. So I hope at this point I've convinced you that there is no universal detector. Every detector has strengths and every detector has weaknesses. Some compounds will detect one compound better than another. And our goal is to use the best detector for detection of each compound. I again emphasize that we're not going to combine these detectors in any sense for data interpretation beyond simply applying them all. We want to apply them and use the best one in each case. So I'm now going to turn my attention to how we do that. How do we evaluate the AET, and how do we accurately quantify using the combined strengths of all detectors? So let's take a practical example. Here we have three compounds that we want to determine if they are above or below the AET threshold. In blue in this figure, or in this table, are the detectors that are most commonly applied, LCMS and GCMS. And in green, I have the orthogonal detectors, CAD, UV, and FID. In the table, I am showing the RRF value for each one of the compounds on each detector. And I want to remind the listener that if the RRF value is greater than 1, that means the response for that compound on that detector is going to be greater than that of the surrogate standard. If that is the case, if the response of the compound is greater than that of the surrogate standard, then a UF of 1 is all that is needed in order to successfully register that compound as above the AET threshold. All right, so let's take the first of the three compounds, bis-2-ethylhexylphthalate. And for this compound, we can see that in LCMS, GCMS, and FID, we have responses greater than 1. This means that no UF is needed in order to register this compound as above the AET, so long as we use any of those three detectors. If we use CAD and UV, we see that the values are below 1. That means some UF would be required, and in this case, a UF of 2 would be sufficient to make sure that these compounds register as above the AET on those two detectors. Now let's consider 5-amino-1-pentanol. This compound gives a relatively poor response in LCMS and GCMS, and we see that a UF of 8 would be required in order to register this compound as above the AET using only those two detectors. But there's good news, which is that the CAD provides a RRF value of 2.5, meaning that this compound can be registered by CAD using a UF of only 1. And thus, we do not have to resort to uncertainty factors to successfully capture this compound. The last compound I want to look at is 1,3,5-triphenylbenzene. And you will note that this compound does not respond in either GCMS or LCMS. This is a strong demonstration of why a multi-detector strategy provides unique advantages, because we can detect this compound without even applying a UF so long as we have a UV detector. But no UF would be protective for this compound if we used only the combination of LCMS and GCMS. All right, so those are some nice examples, but how does this correlate with the entire results for the broadly constituted database of extractables that we analyzed? And we show that in these two figures. On the left-hand side, we have the RRF value plotted on the y-axis with the number of compounds on the x-axis. And this is for the combination of GCMS and LCMS only. And what we've plotted is the larger RRF value, whether it was LCMS or GCMS. So whichever one is bigger, that is the one that was plotted. And we can see that only 54% of the compounds give a response that is above that for the surrogate standard, i.e. that compound would register as above the AET when using the combination of LCMS and GCMS only. If we increase that UF to 2, we can improve that coverage to 85% of the database. Now, if we instead apply the full multi-detector strategy using all of the orthogonal detectors, we see that that coverage improves significantly to 76% for a UF of 1 and to 94% at a UF of 2, which is a very significant degree of coverage for even a relatively modest UF of 2. Well, you may say to me, Mark, that's great if you have a multi-detector, but what if you don't have all of those detectors? Here on this slide, we plot the results for the database of extractables for different configurations of detectors at different UF values. And what we can see is that if we apply a UF of 1, the highest extent of coverage that we can obtain is only 75%, which does not seem to be sufficient. But if we apply a UF of 2 with at least one orthogonal detector in addition to LCMS and GCMS, we can obtain greater than 90% coverage of the database, no matter which one of those orthogonal detectors is applied. If, on the other hand, we apply a UF of 3, we can obtain greater than 95% coverage using one orthogonal detector and greater than 97% coverage for the full multi-detector solution. Now, I want to turn my attention away from evaluation of the AET to quantitative accuracy and how the multi-detector solution can be used to improve quantitative accuracy. Here we have two different graphs. The one on the left is showing us the most accurate RRF value, i.e. the RRF value closest to 1 for the combination of LCMS and GCMS. And we see that only 33% of the compounds in the database have an accuracy within plus or minus 20%, even if we use the optimum detector between GCMS and LCMS. And 55% of the compounds are within 40% of the true answer. Now, contrast that with what we can get if we use UV CAD GCMS FID. And you'll note that I've left out LCMS for reasons I'll explain shortly. If we use this combination of detectors and we select the RF value closest to 1, we obtain a result where 40% are within 20% of the true value and 72% are within 40% of the true value. This is a significant improvement in the quantitative accuracy just choosing the optimum detector. Also importantly, only 7% of the compounds are significantly underestimated, which is of course the worst outcome. Now, obviously, we're not satisfied with that level of quantitative accuracy, but there's another means we can use to improve this, which is a selection of appropriate surrogate standards. Here I have an example of two potential surrogate standards, bisphenol A and ergonox 245, and two target compounds, bisphenol A diglycidyl ether and ergonox 1010. Most of us, I think, would agree that if we were quantitating bisphenol A diglycidyl ether, the most relevant, chemically relevant standard would be bisphenol A. And we can see that if we use that standard and UV detection, we obtain a value that's 83% of the true value, a respectable level of quantitative accuracy consistent with what is listed in most of the guidance documents. On the other hand, if we're quantitating ergonox 1010, we want to use ergonox 245, which is the more similar chemistry. And in this case, we get a value that's 92% of the true quantitative value. If, on the other hand, we were to substitute that out and use bisphenol A, for instance, we get an answer that's only 32% of the true value. So this is a good example of why appropriate surrogate standard selection is important. If we apply the appropriate surrogate standard, then we found that for the database of compounds, 85% of the compounds could be were within 20% of the true value, and 91% were within 40% of the true value. Most importantly, we found that none of the compounds were significantly underestimated. All right, now I mentioned a minute ago that we did not use the LCMS for relative quant. Why? Well, the reason we did not is that it is our belief that we cannot adequately correlate the choice of a surrogate standard with the appropriate target compounds based on chemistry. And so when we look at these same examples we did just a minute ago using LCMS, we see that if we try to analyze bisphenol A diglycidyl ether using bisphenol A, that the two compounds do not even ionize in the same mode. One ionizes in positive mode and one in negative mode. Therefore, we cannot do relative quantitation using bisphenol A as a surrogate standard. Now, you might say to me, well, Mark, yeah, but I could have predicted that because bisphenol A has a phenolic group that bisphenol A and diglycidyl ether doesn't have. And I would say, well, yes, that's true, but let's consider the other example. Here we have ergonox 245 and ergonox 1010. And we can see that both of these compounds have very similar chemistry. Both are hindered phenolics, both have ester groups in their backbones, and they're both relatively large molecules. If I then try to analyze the ergonox 1010 using the ergonox 245 through LCMS relative quant, I see that the highest quantitative accuracy I can get is only roughly 15%. That's because these two molecules actually ionize to significantly different extents and therefore give significantly different responses, even though their chemistry would be considered to be similar. All right, I now want to conclude by summarizing our findings in relationship to the AET evaluation. And I would first just say that there are definitely advantages to targeted analysis in terms of quantitative accuracy, in terms of specificity of a method. But we need to remember that extractables screening and even leachable screening analyses are just that. They're screening analyses, and they therefore need to be broadly applicable and able to capture compounds that are unexpected. If we do get a weak response on any one detector, it is my position that the best way to capture that compound is not through the use of UF, but rather to apply a better responding detector. Because as long as every compound gives a sufficient response on at least one detector, that compound will be included in our study and captured. If we used a UF of 2, we found that for our broadly constituted database of extractables, we can obtain 94% coverage using the full multi-detector solution. This was equivalent to applying a UF of 10 for LCMS and GCMS only. And this mitigated, therefore, the need for the large uncertainty factor. This allows us to avoid needing to apply unnecessary large amounts of concentration. I would finally note that RF databases are needed for proper standard selection and for determining appropriate UF. And lastly, that standards of chemistry that is relevant to our device can be used to qualify the method on an individual analysis and for an individual device. In regards to quantitative accuracy, we would note that having multiple detectors allows us to pick a detector for quantitation which has less RF variation, and thus is a means for improving quantitative accuracy. We'd also, again, highlight the importance of appropriate surrogate standard selection. When we applied this approach to the database of extractables, we found that 85% of the compounds were within 20% of the true value, and no compound was less than 60% of the accurate value. RF databases are important, but they are limited in that they are only helpful for compounds contained in the database. We would also note that UF values do not correct for quantitative inaccuracy. Finally, we think it's important that E&L labs confirm the abilities of their methods to obtain reasonable accuracy for a broad range of compounds, some of which are not in their database. Finally, if you enjoyed today's talk, I just want to refer you to our publication, which came out earlier this year, entitled Reducing Relative Response Factor Variation Using a Multidetector Approach for Extractables and Leachables Analysis to Mitigate the Need for Uncertainty Factors. You can find this in the Journal of Pharmaceutical and Biomedical Analysis. Lastly, I would be remiss if I did not note the tremendous contributions of all of my colleagues at Jordi Labs who worked tirelessly to collect all the data necessary to evaluate the effectiveness of the multi-detector solution. Thank you so much for your attention, and with that, I will turn it back to the moderator.